we are going to go over the quizzes. So if you want to pull this up live and watch this, and you can see that each question going on individually. Question number 1, a group of 125 truck owners were asked what brand of truck they own and whether or not the truck has four-wheel drive. The results are summarized in the two-way table given below. Suppose we randomly select one of these truck drivers. What is the probability that the person owns a Dodge or has four-wheel drive? So Dodge, got 20 and 10. And then four-wheel drive, we also have these two. Now we don't want to count the 20 twice. So we basically have these four numbers added together. And our overall probability, or our denominator is going to be 125 because it's just selecting a truck. So it's out of 125. And if we add those together, that's going to be 60, 70, 80, 90. So that's going to be 90 out of 125. There you go. Question number 2. All right, same table. Question now changes to what is the probability that the person owns a Chevy given that the truck has four-wheel drive. So this is probability Chevy given four-wheel drive. So that's going to be the same as the probability of Chevy and four-wheel drive, which is 32 out of just the four-wheel drive. Remember, it's probability of Chevy and four-wheel drive over the overall four-wheel drives. That's how you do the givens, divide by the givens. So it's going to be 32 divided by, we got to add these up. So whatever 32 plus 28 plus 20 is, well, these are going to add to 60 plus 20, so it's going to be 32 out of 80. And that's number 2. Question 3. A group of 125 truck owners were asked, same scenario. So let me go ahead to this, skip to this part here. Which of the following is true about the events? Owner has a Chevy and owner's truck has four-wheel drive. The two events are mutually exclusive and independent. So to test for mutually exclusive, we just got to look for overlap. So if it's got overlap, they're not mutually exclusive. So we have overlap. We have Chevy and four-wheel drive. They share combination here, right? So if you think about a Venn diagram, Chevy, four-wheel drive, there's going to be some of those in the four-wheel drive that are also in Chevy, and that's that 32. So they're not mutually exclusive. Now we can test for independence by doing one. We test the probability of one versus the probability of one if the other affects it, which is the same thing as the probability of Chevy. We see what that is. And then we find the probability of Chevy given that it's got four-wheel drive. So we find the probability of Chevy given four-wheel drive. So let's find probability of Chevy first. That's going to be combined 32 and 18 over 125. And using my calculator, that gets me 32 plus 18, that's 50 divided by 125.4. So now let's test to see if the probability of Chevy given four-wheel drive is also 0.4. And we did that already in the previous one, didn't we? So that would be 32 out of 80. 32 out of 80. Remember, it's this overlap over just the four-wheel drives, which is 80 total. Well, that should be 0.4 as well. It is. So since these are both equal, that means they're independent. That means that four-wheel drive does not affect the percentage of Chevys. All right, they're not affecting one another. So to summarize, they're not mutually exclusive, but they are independent. Not mutually exclusive, but they are independent. Next question. A spinner has 3 equally sized regions, blue, red, and green. Johnny spins the spinner 3 times and gets 3 blues in a row. If he spins the spinner 297 more times, how many more blues is he likely to get? Well, don't worry about the 3 out of 3. Hot hand doesn't work here. Each probability is equal chance of being selected. If we have, you got your red, blue, and green. Red, blue, and green. You spin that however many times, we would expect about each one to be a third of those spins. It's not going to be, but the expectation is that would be the most likely result to happen. So each is about a third. I'm not going to change color here, but you're just going to take your number of spins and divide by 3, and that'll get you each one. Well, that's 99. So we would expect each of them to be around 99. Does that mean they're going to be 99? No, but that's the expected value. That's about as much, that's the closest we would, the most likely outcome to happen. Next question. All right. Wilt is a fine basketball player, but his free throw shooting could use some work. For the past 3 seasons, he has made only 56% of his free throws. His coach sends him to a summer clinic to work on the shot. When he returns, coach has him step to the free throw line and take 50 shots. He makes 34 shots. Is this result convincing evidence that Wilt's free throw shooting has improved? We want to perform a simulation to estimate the probability that a 56% free throw shooter would make 34 or more in a sample of 50 shots. Which of the following is the correct way to perform the simulation? Let integers from 1 to 34 represent making a free throw, and 35 to 50 represent missing a free throw. So think about this. This is 34 out of 50. That's 0.68. That's not 50. We want to simulate 56% chance of being made. So it's not going to be this one or this one. Okay. Our goal is to look at his original percentage, 56%, and test that over and over again to see if he can get 34 shots made. So let's look at this last two. Let integers from 1 to 56 represent making a free throw. So 56, make, and 57 to 100. So those 44 would be missed, but overall there's 100 shots. So the percent of making it is 56%. So now we're comparing that here. Let integers 1 to 56 represent making a free throw. 57 to 100 represent missing. So again, 56 out of 100 represents the original probability, 0.56. So now we can simulate with those numbers. And they're very, very similar. The only difference is one talks about repeats or not. It says generate 50 random integers from 1 to 100 with no repeats allowed. Count the number of made free throws. Repeat this process many times. Versus generate 50 random integers from 1 to 100. Count the number of made free throws. Repeat this process many times. Now listen, guys, if you're paying attention, I have the answer wrong in the answer key. Unless I correct it for B-Day, I'll correct it for B-Day. But if you're A-Day, it's telling you the wrong answer. It's going to say this with no repeats allowed is the right answer. But we can do this with repeats, okay? You can keep simulating this. If you get a 46, and a 46, that just means made, right? You get a 46 twice, this is 2 made shots. You can repeat that. So you actually are allowed to have repeats. And then we want to count how many free throws. So you do 50 random integers. We want to see, do we get 34 out of those 50 shots being made? How often does that happen? Graph it out. So it is going to be this one, even if it says this is the right one, okay? It's going to be this purple one here. I promise you that's the right answer. Now let's look at the next question. The dot plot displays the number of made shots in 100 simulated sets of 50 free throws made by someone with probability of 0.56 of making a free throw. What's an appropriate statement about Wilt's free throw shooting based on the dot plot? If Wilt were still only a 56% shooter, the probability that he would make at least 34 of his shots is about 0.03. So in other words, he made 34 there, 35 there, 36 there, that's 3. Remember how many times we did this? 100. At least is 34, 35, or 36. So 3 out of 100 is 0.03. So that seems like that's right. Let's go back and make sure we know why the other ones are wrong, okay? So if Wilt were still only a 56% shooter, the probability that he would make at least 34 of his shots is 0.097. This would be at most. This would be 30, or not even at least 34. This would be less than 34, which obviously is not what the question wants to know. We want to know, can he get 34 shots or more? So it's not going to be that one. If Wilt is now shooting better than 56%, the probability that he would make at least 34 of his shots is about 0.03. We're not saying he's shooting better than 56%. We're saying he shoots at 56%. Now we want to use our simulation as evidence to prove that he's better, but we haven't proved it. Haven't proved it. And that's the same thing here. Haven't proved. Wilt's not shooting better than 56% yet. Our simulation is going to help prove that, help us discuss that. So let's look at the last one. If Wilt were still only a 56% shooter, the probability that he would make at least 34 of his shots is about 0.01. Well, no, that's exactly 34. Not at least. At least is 34, 35, or 36. So it's going to be this one here. Number 7. Oh, a probability distribution. They always add to 1. 1, 2, 3, 4, 5. These are scores on an AP test. 10% got 1s, 20% got 2s, an unknown percent got 3s, 25% got 4s, and 15% got 5s. Let's figure out that. So the probability of 3 is going to be 1 minus probability of 1 or 2 or 4 or 5. So let's add those up together. 0.1, 0.2, 0.25, 0.15. All right, my calculator tells me 0.1 plus 0.2 plus 0.25 plus 0.15 is 0.7, which means that's going to be 1 minus 0.7, 0.3. There, that was bothering me. Now I got all the numbers in the table filled up. If the student earned a score of 3 or higher on the AP exam, what's the probability that the student scored a 5? So given a score of 3 or higher, so 3, 4, or 5, what's the probability, of scoring a 5 given they score a 3, 4, or 5? Always put your given being divided by, so scratch that over here. So 3, 4, or 5, you just add those together, 0.3 plus 0.25 plus 0.15. That's your denominator. And then your numerator is just the 5 out of that, so it's going to be 0.15. Alternately, you could just say, well, this is 0.3 here, so 1 minus 0.3 is going to be 0.7. That's your denominator. So that does add to 0.7, so this is going to be 0.15 over 0.70. Calculator says that is 0.21428. So That's number 7. Question number 8. Suppose that a student is randomly selected from a large high school. The probability that the student is a senior is 0.22. The probability that the student has a driver's license is 0.3. The probability that the student is a senior or has a driver's license is 0.36. What is the probability that the student is a senior and has a driver's license? Remember this formula here for probabilities. We would say the probability of an event A or B happening is the probability of each individual event happening minus the probability of them overlap, so A and B. So that's the generic formula. Add the overall, subtract the difference, the overlap, and we can plug in what we have. So we know that the probability of A is senior, we can call senior A. So we'll call that A. That's gonna be 0.22. And we know the probability of driver's license, we'll call that B, is 0.3. So the probability that the student is a senior or, so we know the or, that's gonna be over here. But we don't know the and value. So we're gonna call that X. So your equation is 0.36 equals 0.22 plus 0.3 minus X. So if you combine these two, that's 52. And if you subtract those from each other, you'll get 16. So that's going to be 0.36 minus 0.52 equals negative X. Well, that's negative 0.16. But you can't have a negative probability, so 16%. And one more question, number 10. The security system in a house has 2 units that set off an alarm when motion is detected. Neither one is entirely reliable, but one or both always go off when there is motion anywhere in the house. Suppose that for a motion in a certain location, the probability that detector A goes off and detector B does not go off is 0.25. The probability that detector A does not go off is 0.35. What is the probability that detector B goes off? This problem, unless you see it drawn out, needs to be visualized. Okay, so it's gonna be hard to kind of understand what's going on here until you think about maybe a Venn diagram. So we'll start with these 2 Venn diagrams, and suppose that for a motion in a certain location, the probability detector A goes off and detector B, so we'll say probability of A goes off, and this would be the probability of B goes off. Now, one or the other or both will go off. So there's nothing going to be on the outside here. Everything's going to be in these circles, because it says suppose that for a motion in a certain location, and it says the security system in a house has 2 units that set off an alarm when motion is detected. So if there's motion, one of them is going to go off. End of story. So now we have some Venn diagrams we can fill in. So the probability that detector A goes off and B does not go off is 0.25. Well, that's going to be just in this portion. Okay, A goes off, but B does not go off. That's over there on the left side. So 0.25 right there. Let's look at the next one. The probability that detector A does not go off is 0.35. Well, A does not go off. A's going off in here. A's not going off there. Right? So that means B, if A's not going off, B's going off, right? So but just this portion of B that's not part of A. So that's going to be 0.35. So we want to know, what is the probability that detector B goes off? Well, detector B could go off also when A goes off. So we have to figure out this missing number. And remember, everything adds to 1. So 0.25 plus the both plus the 0.35, that should be 1. So this is 55%. Wait, 30 plus 20 is 50. Sorry, that's 0.6. So the both is going to be 0.4. 1 minus 0.6 is 0.4. So now I have that. And probability of B going off is all of that. So it's going to be the 0.4 plus the 0.35. So there you go. Thanks for watching.